Hey, you're just in time for 3-9. Derivatives of exponential and logarithmic functions. The last two that we will look at in this chapter, last section. Here we go. It's Alan. Now, because we're looking at these two exponential and logarithmic functions, we're going to focus in on some of the better looking bases that both of these work well with and that are very important to us. And now you'll actually see why. And that's called the natural exponential number, or Euler's number, named after the fellow that discovered it, and we represent it by the letter E. Some argue it's because of his last name, others because of where it came from, and that's an exponential function. Either way, we're going to start with that in exponential functions, and then we'll work our way to logarithmic with also using that natural exponential number, E. So some of these I will show the proof of, others I will not, just because I feel like some are better than others, easier to understand, and hopefully will benefit you. So we're still, remember, in chapter 3, I know, last one, and therefore going to be looking at the derivative of these last two functions, which remember have many options for bases, typically positive and not one, but we are going to focus on E, which is, remember, a little less than 3. The derivative of e to the x is, you'd never guess it, itself, e to the x. Again, one of the special things about this number is not only that, but also the fact that when we plug in a 0, we get an answer of 1, which means when we plug in 0 to the derivative, we get a nice slope of our tangent, the nicest, a 1. Some may argue 0, but many things give us that. Now, remember, we also talked about if it wasn't just an x up in the exponent, what if we also had another function? Well, we know the derivative of e to the x is e to the x. So what would you think e to the g of x, its derivative would be? You're right, it is also itself. But if you read my little hint here, due to the chain rule, we also would have to therefore take the derivative of the exponent. We did the e to the x part, but we did not do the x. And again, if you wanted to do it up here, you know the derivative of x with respect to x is just a 1. So we just get that. But here, when it's more than just x, it's some other function, we must also take the derivative of that. So that is the natural exponential. Let's take a look at the natural logarithmic function and its derivative. Theorem 3.9, 2a and b. Again, if we just had x versus g of x, an entire function, what would the derivative of those things be? Some of you probably guess, well, it's just ln of x. Unfortunately, it's not that simple. It is still fairly nice. So I'd like you guys to take our function, which I'm going to write in simpler terms, y equals ln of x, and I want you guys to try and prove what the derivative of that would be. Go ahead and pause it, give it a try on your own. Otherwise, I'll go through it with you here shortly. All right, so taking the y equals ln of x instead of f of x, just an easier way to write it. Knowing that the ln has a base of e, that natural number or natural log, then we can do the log or inverse to rewrite it in exponential form. Now, why that? Well, we already know that. But by that, I mean we want to take the derivative. So I will now take the alternative form of my logarithm in exponential form, and I will take the derivative of both sides of this thing with careful respect to x. And that's simple on the left side. We know the derivative of x with respect to x is just 1. But careful on the right, e to the y, we know the derivative of e to any power is that thing. But we'd also have to take the derivative of that. And remember, that was what we actually wanted. So again, because it's multiplying, we will go ahead and divide by our e to the y, which all cancels out to be a 1. And now I have what my dy dx is. It's 1 over e to the y, which we said was equivalent to just writing x. And since we like it with respect to x, we're going to keep it as that because it's easier anyways. So that, my friends, is the proof of what the derivative of our natural log of x is, 1 over x. But of course, what if we didn't just have x? What if we had another function? Instead of natural log of that just being 1 over that, we will have the natural log of some function. The derivative of that is 1 over that function, but also times the derivative of that function. Again, our chain rule at work, doing the outside first. Natural log of something is 1 over that something, as we just saw here. We also have to do the derivative of the inside, which is our chain. So if you'd rather use the u substitutions to make it look a little bit cleaner, easier to write, and that way we don't have to memorize 2 for all of these things, here's what they would look like. We would now have e to the u if we replace that g of x, and natural log of u in place of that g of x. Again, just a little bit easier. Remember, we said that the derivative of e to a power was e to the power. But remember, that's only the derivative of e to the power. We still need to take the derivative of that power, which, hey, we can't forget about u. So we will just put du. Now, of course, it should be du over dx, but you guys get the idea. And if it's the natural log of u, remember we said that that is 1 over u times the derivative of u. Now, I actually like to write it like this and not simplify. Some instructors, some books will actually write it as if they put it over 1 and have du over u, which is true. It is a completely true statement, but I much prefer this because it makes more sense with everything that we are doing. And hate to break it to you, there will be a time that we want to take this and work backwards. Okay, don't freak out. We'll get there eventually. But for now, there is a reason why I'm having you write it like this rather than what seems like a simpler, more condensed version. So this is how I will use and say these from here on out. That way we can just memorize these 2 rather than the other 4. Using the u's is a little bit simpler. Now, of course, there's many other bases other than this natural number e. So we do have to explore those as well. But if we have a choice, we will always choose e and natural log for that base of e because these turn out really nice. So then how would you come up with the proof of when it's any base for any logarithm? Let's start with that one and let's find the derivative of that. Go ahead and pause it, give it a try, see if you can come up with it. You're welcome to use anything that we've already talked about. Good luck. Okay, hopefully you came up with something here. It's going to be very similar to what we did previously, where we just let the f of x be y, rewrote this, and then I took my log form and rewrote it in exponential, just to get rid of my log, doing the inverse, flip-flopping the x and the y. So now I have x equals b to the y. But what's peculiar is I'm actually not going to leave it like that. I actually want to get this exponent down out of that area. And by doing the natural log to both sides, I can now bring that down. And so on one side, we have the natural log of x. On the other side of our equation, we have y times the natural log of b. And then we are going to go ahead and divide by the natural log of b so that those cancel out. And I've now isolated my y once again so that I can take the derivative. And if you notice how I rewrote it, I actually expanded this out and said 1 over the natural log of b times the natural log of x is what my y was equal to, because this is simply just a constant. And we know that a constant times a function, when we take the derivative, we can just focus on taking the derivative of the function and still multiplying by the constant. So when we actually finally take the derivative of this thing on both sides with respect to x, we get that, which can be condensed, multiplied across, and we get very similar to our natural log, which, remember, the natural log of x, its derivative was just 1 over x. So the only thing that we have in addition is down in the denominator. It's not up top. It's not out to the side. It's down in the denominator. We have to multiply by the natural log of our given logarithm's base. Okay, cool little proof. I feel like it makes a little bit more sense once you've seen why it is what it is. Just another thing that we have to memorize and or be able to access quickly. So a few others, 3b and 3c are virtually the same, whether we write it as the log of another function inside of that, or just call it u. We know then that the derivative would be 1 over that inside thing times, still again in the down in the denominator, natural log of b, but now also chain rule times the derivative of that inside function, g prime of x. Easier said, the log of u, its derivative, is 1 over u times the natural log of the base times the derivative of u. Again, should be written as du over dx. It's just easier to put the derivative of u. To piggyback off of the logarithm stuff, with any base, let's talk about, instead of a base of e, what would happen if we had some other base? Again, positive, but not 1. Could we rewrite this or find the proof of it? Proof of this one, very similar. If I have y equals b to the x, I can just take the natural log of both sides to get that power down in front. Now I have the natural log of y on one side, and then x times the natural log of b, which remember, that is just some constant. So I can just take the derivative with respect to x on both sides, and I have some constant times x, which is just 1 times that constant, and the derivative of the natural log of y is 1 over y times the derivative of y. So to get that by itself, all we had to do was multiply over both sides by the y so that these cancel out, and I got my derivative. Only thing is, we would like it all with respect to x. So instead of the y, we said what y was equal to at the very beginning. We can replace it with b to the x. So we literally have the same thing that we did when we had e to the x. It's itself again, but just like we had when it was the natural log of u, it was just 1 over u du. We had that addition of multiplication with the u by the natural log of b. Well, we have it again here. It's b to the x times the natural log of b. So filling out these, I prefer b to the u over g of x. But either way you get, so these are things that we will come across from time to time, but if we have a choice, as you can see, not quite as nice as when we use that natural base or number of e. So we're almost there. This is the last topic of discussion for not just this section, but also this chapter. And it is obviously very important. So don't brush it off. I know it's been a long chapter. Hang in there, guys. We're almost there. In order to talk about this, I wanted to make sure that I reviewed. You can see all the way from 1.5, some properties of logarithms. The big three, the product, quotient, and power. If you can write those down before me, go for it. Otherwise, these are the rules that we discussed not only in this class, but almost all the previous ones. Algebra 2, pre-calc, college algebra, because we are going to have to use these. Knowing these will actually allow us to take very complex functions that we're asked to find the derivative of and just use some of these things to either take and condense down into smaller, easier things to work with, or even get powers down so that we don't have exponents. But don't forget, we're going to choose a base of e so that we're using the natural log because that derivative was way nicer. And hopefully you also remember that we cannot just have a log on one side of our function or equation. We would have to take it to both sides. And if we're only given a function, there aren't two sides. There is not an equation. But remember, we can always say that any one of these things is equal to whatever we want. If you're asking why, you're absolutely right. Now I'd have an equation and two sides. And now I can take the natural log of both sides and do what I want to do to this side to try to make it simpler. So the last thing for this section, for this chapter, are some blanks that I'd like you guys to try to fill in. Just think about these things before I just give them to you. 5 steps in order to make really involved functions a little bit simpler. So in order to differentiate some function, we're going to take the natural log of both sides in order to obtain the natural log of our function. That hopefully we can take that nasty old function and use what we know the rules of logarithms are in order to condense it, make it a little bit simpler, not as nasty. So that's part 2. Well, then part 3 says to do what to both sides of the equation, and leaving the left side as, well, don't forget our goal. Our goal is to differentiate. But we now have, if we didn't have one before, an equation. And we'd have to take and differentiate both the left and the right, which now takes this natural log of y, the left side, and leaves it as the natural log of u, remember, is 1 over u du. And our goal, remember, was to just solve for that dy over dx. So to get this by itself, we would have to multiply both sides of the equation by y, not why, but the letter y. And because it's all with respect to x, we'd rather not have this on the right side anymore. But remember, at the very beginning, they told us what y was in terms of x. So all we have to do is replace that y with whatever our function is. They're calling it h of x for this example. And now we will have the entire right side in terms of our x. So I know that seems like a lot. You will get better at these with practice, but make sure you practice appropriately and don't just do them incorrectly and continue to make mistakes. Be nice, neat, and organized. Here's a nice step-by-step approach in order to help you with these. And just to remind you that although this chapter 3 was very, very long, I wanted to remind you that all this differentiating that we did, these are all shortcuts for us finding the derivative compared to what we had to do in chapter 2, which was that limit definition. So the better you understand these, the better off you're going to be in next chapter. And of course, for this exam. So keep working hard. Let me know how I can help. Use the things that you have available to you, our TA, each other, the interweb. Otherwise, nobody can work for you and understand it for you. You just have to put in the time. Let me know if I can help in any way. Otherwise, take care, keep working hard, and I will see you for chapter 4. See ya!